All right, hi guys. So we're talking about the definite integral and how this relates to those Riemann sums we just finished talking about in 5.1. Okay, so let's go ahead and start with some notation here. So we call a definite integral. So you guys remember last um, in 4.10 we were doing indefinite integral. Now we're going to learn what this definite word means. Okay, so the definite integral of f of x from A to B. Or I might say on the interval A to B, right? Same thing. So what this is it's the Riemann sum, but we use our integral notation with bounds, which we haven't done before. Okay. So then it's the Riemann sum here, n equals, not n, excuse me, I equals 1 to n f of xi delta x. Okay. So is this guy here. So yeah, this is the integral from A to B, definite integral. So definite because it has the bounds, right? Remember with indefinite integral, there were no bounds. So the indefinite integral is talking about the general antiderivative. The definite integral, we're really talking about this area. Now, of course, sometimes it might be negative. So we're really talking about the net change in area, the signed area. So net area below the y-axis, x-axis, excuse me, is negative, quote unquote, area. Okay. So, if this limit exists, we call f integrable. It's able to be integrated. It's integrable on A to B. Okay, it's integrable. Okay, yeah. So let's just take a look at the anatomy of this for a second. Okay, so we have this. So these are our bounds or limits of integration. Okay, what interval are we looking at? Okay, again, just to recap, this is the integrand. And then we are integrating with respect to x. Okay, x is the variable we're looking at. Now, right, that tells us what variable we're looking at. The variable doesn't matter though, right? So if I'm looking at the integral of a to b of f of x dx, that equals the integral a to b of f of u du, or the integral a to b f of t dt, right? The variable name can change, but the content of what we're talking about is the same. Okay. That's a very important thing to get used to. The variables do not matter, right? Same with limits and derivatives and things like that. Okay. Okay. So we already did an example last time. So C end of 5.1. Um, we showed that the integral from 0 to 2 of x squared dx, that was 8/3. Okay. So remember we did the Riemann sum. We didn't write it with this notation, but that's really what we did, right? The Riemann sum in the limit that equals this integral we're talking about. Okay. So let's go try another example. Let's look at integral 0 to 3 of 2x minus 1 dx. Now, um, we want to use the definition of the integral, definition of the definite integral. Okay. So what we're doing right now, if you remember with derivatives, we did that whole limit and the whole fraction and we did all that stuff. Um, it was essentially the long way, but it was why it works. Then we learned all the tricks and we don't do the limit anymore. We learn all the tricks. We're going to do the same thing here, essentially. All right. Yeah. So if you want to try this on your own, the process is going to be basically exactly the same as the example we did at the end of 5.1. Okay. So go ahead and pause here and try this on your own. Look back at the other video if you need to. Okay. All right, so let's go and do this. So remember this integral, using the limit definition, this is the limit as n goes to infinity, sum I equals 1 to n, and then we need f of xi times delta x. Okay, so let's look at the parts of this. So delta x, that's b minus a over n. Okay, so in our case, that's 3 over n. Then f of xi, that's going to be f of x naught plus I delta x. Okay, and we know all those pieces. X naught is 0. I is just I. Delta x is time 3 over n, and that's multiplication. So this is f of 3i over n. Okay. Okay, but I know what my function is. It's 2x minus 1. F of x is 2x minus 1. So this is 2, 3i minus, or over n, minus 1. Okay. So now we can plug all this in. So my integral 0 to 3 of 2x minus 1 dx, that equals the limit n goes to infinity, sum I equals 1 to infinity, and then it's my function part. So it's, well, I can multiply the 2 and 3 together. So that's 6i over n minus 1 times delta x, which was 3 over n. Okay, now let's multiply these things together. Okay, so all this first bit stuff stays the same, but I have, what do I have? 18, I gotta distribute the 3 over n. So I have 18i over n squared minus 3 over n. Okay. Now let's use our properties of sums. Properties of sums. So this is the sum I equals 1 to n of 18i over n squared minus the sum I equals 1 to n 3 over n. Okay. Okay, so we can tackle these together. Maybe I should do some brackets around this for the limit. So let's do some brackets. I can factor out 18 over n squared. That has nothing to do with I. Um, okay, so it's just I in the sum. Here, 3 over n, that has nothing to do with I. So this is, we're adding up 3 over n plus 3 over n plus 3 over n, right? N times. That's 3 over n times n. Okay. Now we can plug in that formula for the sum of I. Okay, we actually proved it last time. So it's n plus 1 over 2, and this guy is just minus 3. Okay, so this is the limit, n goes to infinity. Um, okay, stuff cancels here, right? So one of the n's is going to cancel, and the 18 and the 2 will cancel. So I have 9n plus 1 over n minus 3. Okay, now we have to know that limit, n over n plus 1. Okay, whatever strategy you need to do, that limit is 1. So we have 9 times 1 minus 3, which is 6. And that's the area. Okay, that's the area. Now, let's take a step back here and draw the picture. What do we have? Well, 2x minus 1, that's got a y-intercept of minus 1, and it's got a slope of 2. So here's minus 1, here's 1, here's 3. Okay, so if I go, I have to go up 2 over 1. Up 2 over 1. I gotta go a little further. So let's call this 5, like 2, 3, up 2 over 1. Okay, so that should be a straight line. Okay, now we're doing the integral from 0 to 3. So from here to here, okay, on this interval. Okay, and we're trying to find the area. Now remember, because sometimes the y values are negative, we're talking about the signed area. Area under the y-axis is negative. Above the I keep saying y-axis. Area under the x-axis, right down here, this area is negative, and then the area up here is positive. Okay, maybe I should use green actually for positive. Okay. Notice though, those are triangles, right? So we could have actually done the area the normal way. I won't do that, but what you'll find is if you do, well, yeah, let's just take 30 seconds to do it. So I need to find the base for my triangles and the heights. Okay. The heights are easy. This has a height of 5. This has a height of 1, right? Because it goes -1 down there. So the height of the triangle is 1. The bases, we can just kind of check this out here. So for the big triangle, it looks like 2.5. Okay, 2.5. The small triangle is going to be a half. Okay, so we're doing signed area. So my integral 2x minus 1. My area above the x-axis has positive area, so it's a half times 2.5 times 5, right? That's the area of the green triangle. Then negative, right, minus the area of the red because that's below. So a half 0.5 times 1. Okay. And what do you know? That's going to give you 6. Okay. So we checked our answer. Um, Now, we could only do that because those are shapes we already knew, right? Triangles, rectangles might pop up, but this limit process, the Riemann sum definition, um, comes in useful for everything else. Okay, so let's check this out. Evaluating definite integrals. Okay, so we're going to take a look at a little bit more geometry here. Okay, we're going to take a little bit more look at the geometry. Um, so what's going on? What's going on? So let's look at, oops, excuse me, the integral from 3 to 6 of this crazy function, 9 minus x minus 3 squared dx. So I said we're gonna use geometry. Okay, you could do the Riemann sum formula here, but we have not learned all the algebra skills, and we will not learn the algebra skills needed to evaluate this using that. Okay, we're gonna find other ways, shortcuts. Okay, to deal with integrals. We want to stray away from the limit, right? Because that's got a lot of work. If you guys remember with the derivative, the limit stuff took a while, but once we learned shortcuts, oh my God, it was way faster, right? Similar process here. So, first of all, what does this function actually look like, right? Since we're doing the geometry, we're looking at it geometrically. What are we actually talking about? Okay. So y equals that. So one thing I want to point out here is the square root is can't be negative, right? If I take square root of something, the result will never be negative. So this is bigger than or equal to 0. That'll come in a second. Okay. Now this, I don't know what this looks like. So we're going to do a little bit of algebra, rearrange things around, and it'll turn into something that looks a little more familiar, hopefully. So first I'll square both sides, and I'm going to add x minus 3 squared to both sides as well. Okay. Hopefully you guys know what shape that is. That's a circle. Okay. So that's a circle. My radius is 3. So I take the square root of this guy. My center is at 3 comma 0. Okay. So for x, when we're subtracting x minus 3, or the x coordinate would be 3. On the y, we're not subtracting anything, right? So it's like y minus 0, essentially. Okay. So we can draw that. We can draw that. Um, so the center is at 1, 2, oops, excuse me. X coordinate is 3, 1, 2, 3. So the center is here and the radius is 3. So it actually just um, barely hits the origin there. Okay. And this goes all the way to 6, right? If this is 3, the radius is 3, so it must hit 6. Now, remember what I said, the y the function y is always non-negative. So even though this is a circle, we actually introduced part of the function that is not there. So y equals a square root, whatever, that has to be positive. So we're going to actually only look at the top half because we need y to be non-negative, the y coordinate. Okay. What else? So this is what the function looks like. Now we're only integrating on the bounds 3 to 6. Okay. Remember, these are the interval. This is the interval of my x coordinates. Okay. So x is between 3 and 6. Okay. Well, I can see that right there. So this integral is asking for the area under this curve on the interval 3 to 6. What's the area of that? Okay. Well, we can do it geometrically, right? This is a circle. So the area of the circle is going to be pi r squared. So the radius is 3, so this is 9 pi. However, our integral we care about is not the area of the circle, it's the area of just that shaded region, which is a quarter of the circle. Okay, so this definite integral here is actually going to be 9 pi divided by 4, a quarter of that area of the circle. Okay, yeah, and that's that. Okay. Um, okay. Now we will learn other ways to approach those, not we, excuse me. You're going to learn other ways to approach integrals that look like this next in Calc 2, excuse me. Okay. All right. So go ahead and try this one on your own. It's going to be similar to the other one we did. 2 to 4, 2x plus 3. Okay. Let's go ahead and just pause the video, at least draw it. Okay. And then come back to check your drawing, and then we'll go from there. Okay, so let's draw this. So we're integrating from 2 to 4, so I don't have to draw the left part of the graph. So 2 to 4. And I think I need more room here. Okay, so 2x plus 3. So the y-intercept is already 3. And then we're going a slope of 2 every time. Okay. Just so my picture doesn't get huge, I'm going to scale this down a little bit. Let me pause here and draw it. All right. So this is our function here. Now, I drew some points on there to get the, shape of the line, 2x plus 3, but we're only integrating from 2 to 4, x values. Okay, x values 2 to 4. So I only want that area there. Okay. Now, we could do this. What we want to look for is shapes that we know. Okay. So if you know the area of a trapezoid, this is a trapezoid, right? If you know the area of a trapezoid formula, you could do that. What we can do instead, if you don't know it, is cut right there. Now it's a triangle and a square. Or is it a square? I think it's a rectangle, actually. It looks like a square, but that's because I have a different scale. Um, yeah, so let's get the area here. So we can see the height is 7 for that. And then the height for the rest of this is 4. Okay. And then the width is 2. And yeah, the base is 2 here as well. So our area is going to be 4 times, excuse me, not 4, 2 times 7. That's the area of this rectangle, plus a half, 2 times 4, area of the triangle. Okay. So that's 14 plus 4 is 18. That's our definite integral. Okay. Now, like I said earlier, so the integral a to b f of x dx is the net change in area. It's not simply area, right? Area below the x-axis counts negatively towards it. It subtracts, okay? So we saw that example, this example with this triangle here. Um, okay. Um, yeah. Excuse me. Now sometimes we call it net signed area. Okay. Sign meaning the area. isn't simply the area, but it has the sign attached to it. So it's positive if it's above, and it's negative if it's below. Okay. So as kind of a picture here, if we're looking at a function that looks like this, and I want to integrate on this interval here, this has an area and this has an area. So I'll label them A1, A2, right? That's an A2 there. Um, but when we do the integral, maybe I'll call this x value 4, right? So the integral 0 to 4 f of x dx is not simply a1 plus a2. It's not all the areas added together. It's a1 minus a2. Okay. Area below the x-axis gets subtracted. Okay. So let's try this with an example. Excuse me. So let's find the integral negative 3 to 3 of 2x dx. Okay. Um, yeah, so this one we could do the definition of the integral. It would be a lot of work. Geometrically is quicker, right? Especially because I know what 2x looks like. That's a line. I know what that looks like on the graph. Okay. So let's draw it. Now we are integrating from negative 3 to 3, so I do need um, those bounds there. And then 2x, what does that look like? Well, it goes through the origin and it's just a line. Okay. And then got my bounds here. Okay. So again, this is positive area because it's above. This is negative area because it's below. Okay. So this integral, if I call this area 2 and this is area 1, right? So our integral is going to equal a2 minus a1. Okay. Positive area minus the area below the x-axis. Now, let's actually find them. So you can, you know, figure out your heights and your bases. What you'll see is the heights here are both 6 and the bases are both 3. So the areas are actually the same. They're both a half times 3 times 6, but we're subtracting one from the other. So this integral, this net change in area is 0. Okay. One way to think about it is as we move along the bound, so I start here on my left bound. As we move along, so now I'm here, now I go here, I'm accumulating negative area. So far, my integral is negative because I've only accumulated negative area. So I keep going. So then I hit here, I hit the origin, excuse me. I'm done accumulating negative area. There's no more negative area. Now, once I keep moving across my bounds even more, this positive area is counteracting that negative area I already got. So I keep going, keep going. Once I hit the end, all the net change in area, in signed area, um, balances out completely, right? The negative area I have and the positive area I have cancel each other out. Okay. So I want you guys to go ahead and try an example. Now that we see this, check out the integral 0 to 6 of x minus 2 dx. Okay, so do what we did already, or not what we did, but same strategy. Draw the picture, notice which areas are positive and negative, find the actual areas of all of them, and then do this appropriate addition or subtraction. Subtraction if it's below the x-axis. Okay, I'm going to pause here, and then we'll jump straight to the solution. Okay, hopefully you paused. So there's the picture. And in there you can see I calculated the areas and then I did the appropriate subtraction. So positive area minus the area below the x-axis. Wonderful. Okay. So um, if we want to do total area, right? I don't want to worry about these pluses and minuses, right? I just want the actual, all the area, even if it's below the x-axis, right? How do I get that? Well, what I have to do is take the absolute value of my function. So it's the integral a to b of the absolute value f of x dx. Okay? Because think about what we're doing. If we do absolute value, like for example in this problem, this triangle here that's negative, absolute value makes it positive. So it flips up. And now when I do the integral of this guy, both of these areas are positive, right? So they get added together the way we want them to. You get the positive area. Okay. Now I don't want to mess up my picture here, so I'll erase that. But you can pause and go back and think about what I said. Okay. So the absolute value makes everything positive. So then the integral of all positive things is just all the area added together. Okay. So that's that. Okay. Now let's jump to properties of integrals. Okay, so we've talked about properties of limits, derivatives, sums. Now let's do integrals. Okay. Okay, so I'm going to write some stuff down and we'll fill in the answers together. All right, I've written some stuff here. Let's do the first one. Integral from a to a of f of x dx. Okay, what is that going to equal? Well, a to a, right? Those are my bounds of my x values, but they're the same number. Okay. So there's no area, positive or negative. There's no width in there to have a value. So this is just going to equal zero. Okay. I mean, if you try to draw a picture of a function, okay, I'll start my integral at a, and then I'll end it at a. There's nothing there, right? So that integral is zero. Okay. Now this is an interesting one. Notice here for the second one, we've switched our bounds. The bound switch. So this is another counterintuitive thing that you wouldn't really think about. So it's another thing where if we have area under the x-axis, that's negative. But when we switch our bounds, you could think of it as switching the kind of direction we're going, right? So if I have an integral a to b, right? So the lower bound is A, the upper bound is B. You could think going left to right normally. So that's fine. If we switch the bounds, we're essentially thinking of it as B going to A. Okay, so we kind of switch the order. Now, in reality, it's a little bit more complicated than that, and there's some theorems that we're hiding behind this. So what I just want you to think about is, oh, if you switch the order of the bounds, you pick up a negative sign. Okay, so I already had that answer filled in. I mistakenly wrote it. Okay, but that's one of these counterintuitive things that I just am asking you guys to accept on high from me that I'm commanding you. Okay. For the third one, same as with everything else. When you have a plus or minus, when you're doing plus or minus in the middle of an integral, you can break it apart with a plus or minus, keeping the same sign, whatever it was. Okay. Then this last one here. Right, constant multiple, same as with everything else. We can factor that out. Okay. Then this one's kind of picking up uh, kind of an analogy from the sum thing. But if you think about doing an integral going from A to B, that's the same as going from A to some point in the middle, and then from that point in the middle to B, right? If I have an integral of a function, A to B, well, I could just cut it wherever I want at some point C. And if I do the integral of both those parts separately, that's still the same thing. So this integral is equal from A to C of f of x dx plus C to B f of x dx. Okay? As long as C is, well, C can actually be anything, but yeah, intuitively, C is in the middle, right? Okay, awesome. So let's get some practice with this. Using all of those rules, um, rewrite, so the integral -2 to 1 of -3x cubed plus 2x plus 2 dx. Rewrite that as a sum of three integrals, three separate integrals. Okay, hopefully you paused. So what that's going to be is the integral -2 to 1 of -3x cubed dx plus integral -2 to 1 of 2x dx plus integral -2 to 1 2 dx. Okay. So it's just like with derivatives. If you're doing a derivative of a sum of a whole bunch of stuff, just do each piece individually and then stick all those together, right? So we're carrying over our intuition here from derivatives. Okay. Let's look at something else. Um, let's say we know the integral from 0 to 8 of f of x dx equals 10, and we know the integral 0 to 5 f of x dx equals 5. What is the integral 5 to 8 of f of x dx? So we're going to use another one of our properties. Okay. What I want you to notice here is these bounds are not a coincidence. Okay. So specifically, the integral from 0 to 8 of f of x dx, remember we can split it in the middle wherever we want. So let's split it at 5. So 0 to 5 f of x dx plus 5 to 8 f of x dx. Okay. Now we know two of these. This guy is 10. This guy is 5. The other one is what we want. So we just subtract 5 to the other side. The integral 5 to 8 f of x dx is 10 minus 5, which is 5. Wonderful. Okay, awesome. Let's look at an interesting use of the integral. Let's look at the average value of a function. Okay. Okay, so as kind of an analogy, um, as an analogy, if we're doing the find the average of 1, 2, 3, and 4. Okay. How would you do that? Okay. You may not remember. It's okay if you don't. But what we do is we add up all of the um, numbers and we divide by how many numbers there are. Okay. So in this case, this is going to be 10 over 4, which is 5 over 2. Okay. So this is the average of all of those numbers. Okay. Now, when we're talking about a function, this is a continuous function, right? So if I'm talking about a function, again, I'll draw my classic function I always draw. There's infinitely many points here, right? For y values. So how am I going to find the average y value here? Average value of the function, right? Average y value. Well, one way I want you to think about it is just even though there's infinitely many y values, intuitively, what we would do is, okay, let's add up all the y values and divide by how many y values we have. Okay. Now, again, because we're dealing with infinity here, we can't just simply do it like that. However, um, what we can do is approximate it, right? So, um, if we're looking at the sum of y values, that's the sum I equals 1 to n of f of x I, right? So we're doing an approximation. And then how many y values are there, right? We're going to divide by how many y values we have. Okay. Well, it's just n, right? We have n points. Okay, so this is n. Okay. Okay, so what we're going to do is we're going to recall delta x is b minus a over n. So I can multiply n to both sides and divide by delta x. Okay, so this is really b minus a over delta x. This is really the only time we'll see it written like this, but it will be useful. Um, the reason is we're doing an approximation, right? As we do more and more and more points, n is going to infinity, but b and a and delta x, um, we'll be able to, manipulate this a little bit. Okay. So the average value of f of x on the interval a to b. So this is approximately, we just divide what we have. So the divided by b minus a over delta x. Okay. Right. We add up the y values, divide by how many we have. Now we're just using a different expression for n, but it's still that. Okay. Now we can multiply the top and bottom by delta x. So this is approximately 1 over b minus a, right? We're dividing by b minus a, so that's in the denominator there. And it's f of xi times delta x. What is that sum, right? So remember, this is an approximation. To get it more accurate, we're going to do a limit. So this equals the limit n goes to infinity, 1 over b minus a, and then this sum. Okay. But remember, not infinity. I don't know why I'm keep writing infinity. N f of xi delta x, right? That 1 over b minus a is just a constant. We can factor it out. But the limit and the sum, that's the integral. That's the integral. So it's the integral a to b f of x dx. Okay. So this is our average value of our sum. It's the integral on the interval, but we divide by b minus a, right? B minus a is the length of the interval. So let me give you guys an example, and I want you guys to try one as well. So let's look at find the average value of f of x equals x plus 1 on the interval 0 to 5. Okay. So um, this is going to be 1 over 5 minus 0 integral 0 to 5 of x plus 1 dx. Okay. Now again, we can, draw the picture of x plus 1. So y-intercept 1 and then it's x. Okay, and then our interval is 0 to 5. So we need to find this area. That's going to be our integral. So just like before, we can cut it. So this is a rectangle of height 1, because that's where my y-intercept was, and width 5. Then the triangle has height. Well, this y value here is 6, but the height is only 5 because it only starts here. Okay. And the width is still 5. So this is going to be 1/5 times. So the area of the rectangle is 1 times 5 plus, and the area of the triangle is a half. 5 times 5. Okay. So this is going to be 1/5. 5 plus 25 over 2, and you can chuck that in your calculator and you'll find this is 7 over 2. Okay. So this is the average y value of our function. And what you'll find is in this case, it is what we intuitively might think it is. This is my function here. So what's the average y value? Well, it's probably going to be the thing in the middle, right? The thing that balances everything out. That's the average. Now with crazier functions, you won't be able to rely on intuition like that, but yeah. Okay. So you go ahead and try the same thing um, of 6 minus 2x on the interval 0 to 3. Okay. So I'll help you out really quick. So the average value is going to equal 1 over 3 minus 0, integral 0 to 3, 6 minus 2x dx. Okay. So we've learned geometric ways to find the integral, and then, plug that into the formula, and let's see what you get. All right, so here's the answer. So I drew the function 6 minus 2x. The integral is on the interval 0 to 3, so we're just talking about this triangle here. It has a height of 6, base of 3, so the area is 9. And then we just plug in that area for the integral. 1/3 times 9 equals 3. Okay. And again, 3, whoa, 3 is smack dab in the middle there. All right, wonderful. Thank you guys.